Welcome to the Springs and Masses simulation. A mass attached to a spring is an example of harmonic oscillation, one of the most important concepts in physics. Here, you will investigate the main properties of the oscillating motion of a mass on a vertical spring and learn one of their many applications. This simulation using the lab pad as an important way to... Perfect! I'm Dr. One, the lab assistant, and I will... Let's get ready for your first... Find the lockers and open them to pick up a coat. Click on the door to enter the laboratory. Since we're already in the lab, let's not waste any more time and have a look at the oscillating system of Go to Workbench 1. In this lab, the stop button and the springs have some special properties. Click on the stop button to start the When you press the stop button, the spring stops moving up or down. We will call this oscillating, and the spring jumps to its equilibrium position. This will be The springs of this lab look like normal springs, but they are quite special. Physicists would call them ideal. An ideal spring has no mass and moves without friction. Let's find out how they work. But first, click on the ruler. In this simulation, the equilibrium of a mass spring system is defined by the location of the top of the mass. The big ruler will help you to determine the distance from the fixed end of the spring, all the way to the top of the mass attached to it in centimeters. Brilliant scientists like us have to master the physics behind the motion of an oscillating system of springs and masses. Are you up for helping me master this? On the workbench you will find a set of masses corresponding to different weights and two ideal springs, a soft one and a stiffer one. You can choose different combinations of masses and springs and attach them to the stand on their left. I wonder if we can predict which combination of create a mass spring system that has an equilibrium position of 15 centimeters. Interesting. It seems like it is going to oscillate forever. How do you think this is possible? Precisely. An ideal spring moves without friction. This means that when a mass is attached to it, it will start oscillating and never stop if left unperturbed, and if we can ignore the resistance of air, as in this simulation. This type of motion is called simple harmonic motion. Luckily we are in a virtual simulation and we can use our special stop button to stop the oscillation. Stop the spring from oscillating. Good job doing this. The mass spring system you just created has an equilibrium position at 15 centimeters. This is different from the equilibrium position of the unstretched spring when unloaded. Let's find out more of what affects the equilibrium of... Create a mass spring system that has an equilibrium position of 20 centimeters. Click on the lab pad for more information. You got that right. What happens to the equilibrium position if you keep the same mass but you change the spring? You are right. The equilibrium position of a vertical mass spring system depends on the elasticity of the spring. It also depends on the mass you attach to it. This is a consequence of the effect of gravity on the mass, which acts in the same but opposite direction as the elastic force from the spring. Let's find out more about this elastic force. Springs are used in so many things. Think of the springs in your mattress, or the suspension in a car, or even the pen you are taking note with. These springs differ in stiffness and a different load is applied upon them to deform them. One thing remains the same in all these occasions. Hooke's law will define the equilibrium extension of each spring, given its elasticity and the force applied to it. Which law states that the extension of a spring is proportional to the force applied to it? Brilliant. According to Hooke's law, the force needed to extend or compress a spring by a distance is proportional to that distance. Let's measure Hooke's law for the two ideal springs. Check out how the different weights make the mass spring system extend to different equilibrium positions. Derive the spring constant for both springs. The slope of the line you just created is the spring constant, K. The greater the value of K is, the stiffer the spring. The thick dashed line on the display represents the stiff spring and the thin dashed line represents the soft spring. Which mass spring combination allows the largest equilibrium extension?